So Fermat's theorem states that if f has a local maximum or a local minimum at c, then c is a critical number, which means f prime of c is equal to 0 or
Does not exist.
f prime of c does not exist. Okay, so we know that we got a function, we got to find the first derivative of that function. We then need to say, where does it not exist? Or where is it equal to 0? And that's where we want to look to see if there is a local max or min. But not every critical number gives a local max or min. When we determine the critical numbers, how do we know if there will be either a local max or a local min or neither? Locate the critical numbers of the function shown to the right. Okay, so where are we going to indicate these? Okay, so we'll just kind of circle, right? So where the first derivative would be 0, or where it does not exist, right? I think we've kind of covered those off. And what we want to do is state the sign of the derivative for each interval defined by the critical numbers. Okay, so now we've got these intervals, so I suppose I should divide this into intervals. And state, so what's the first derivative in this interval to the left of here? First derivative will be negative. And I'm not going to do that. I guess I should extend these out a bit. In this interval from here to here, we've got a positive. And then here.
Negative.
And then here.
Negative.
And then here.
Positive.
Okay. So, the first derivative test. Let C be a critical number of a continuous function f. If f prime of x changes from positive to negative at C, so we've got to change from a positive to a negative, then f has a local max. Okay, so maximum at C. And so I would just kind of sit there on a test with my hand, just says, okay, slope is positive and slope is negative, and so that's going to give me a maximum, right? If f prime of x changes from negative to positive, then f has a local minimum, right? So from negative to positive, or sit there with your hands, right? So negative slope, positive slope, we're looking at a minimum, right? And that's really, I mean, we've been doing this with the intervals when we draw in the arrow going in the direction of travel, right, from right to left, and just say slope up, slope down, positive slope, negative slope, and we can see that that sort of forms where we have a local maximum or local minimum. If f prime of x does not blank at C, then f does not have a local max or min. So, yeah, it does not change, right? So it stays the same if it's just positive on both sides or negative on both sides. So it does not change sign. A POI. Yeah, so here we have a point of inflection, right? Because with negative slope, it's still a negative slope. Determine the local maximum minimum values of h of x is equal to x to the fourth plus 2x cubed minus 2x plus 5 and sketch the graph. Okay, so we know it's a quartic. We know that it opens which way? It opens up, okay? And therefore it's going to have at least one, it'll actually be at least one absolute minimum, right? But there could be more. And without drawing it, how do we figure out what this thing looks like? Well, we just do what we've been doing, right? So we've got h of x, so we get h prime of x, which is equal to 4x cubed, 6x squared minus 2. That's it, the minus 2, right? Okay, so that actually could be factored a little bit, right? I mean, we could take a 2 out of there. So 2x cubed plus 3x squared minus 1. Now remember, we don't want to lose factors at any point here, although with the 2, it's not going to be any huge deal because 2 will just always be positive. But if we are factoring a negative out of there, you know, we'll end up turning things upside down if we ignore that negative factor, right? Everything will just go backwards. So we just want to make sure that we keep our factors there. It's continuous. It's a cubic, so it's continuous everywhere, right? It's not defined. It does not exist. It exists everywhere. So we need zeros. So how are we going to do zeros? What are we going to do here? Yeah. So well, we could see if we stuck in like what +1. What would we get? 2 plus 3. That won't do it. Put a -1 in there. We'll get like -2 plus 3 minus 1. So I think we can get a 0 out of -1, right? So if we say what, h prime of -1 is equal to 2 times -1 cubed plus 3 times -1 squared minus 1. And let's get -2 plus 3 minus 1. So h prime of 1 is 0. Sorry, h prime of -1 is 0. So then what do we want to do? Well, this goes back to 30-1, I think, right? So if we know that -1 is a 0, then we can do a synthetic division, right? You guys do synthetic division? Yeah, okay. So if -1 is the root, then x plus 1 is the factor. I mean, I write it that way. This is what you maybe see it written differently, I guess. But what are we doing? The 2 cubed, and then a 3x squared, and then no x, and then a -1. 1, 1, -1, 0. I don't know if that matches up with how you guys do this, but you have something along these lines, right? Okay. All right, so what do we want, right? We really want the factored form of this guy, so h prime of x is, we got a 2, we got an x plus 1, we got a 2x squared plus x minus 1. So 2x plus 1. What? Plus, minus, plus. Like so? 2x squared plus 2 minus 1 is plus 1 minus, yeah. Okay. So let's clean that up a little. Got a 2, got a 2x minus 1, got an x plus 1 squared. Okay, so we've got our factored form, right? We've got our factors. I'll put that over. And then we've got our zeros, right? So h prime of x exists everywhere. Or it does not exist, right? Because remember, critical numbers are where it doesn't exist. And h prime of x equals 0 gives us x is equal to what? Half or -1? Okay, so what do we got? Critical numbers are at a half and -1, and we've got the factored form. So what do? We list the factors. So we've got a 2 we've got a 2x minus 1. And we've got an x plus 1 squared. And that'll give us h prime of x. And then h of x. And what did we say they were? Negative 1 and 1/2? Okay, so we just need to fill in our signs. 2, it's just positive everywhere. 2x minus 1. Well, if I throw a big negative in there, that'll be negative, and if I put a 0 in there, that'll be negative. It's positive. You're squaring something, that'll be positive everywhere. All right, so what do we got? H prime of x is negative, and then it's negative, and then it's positive. On the first derivative test, which we hadn't formalized till now, but we've just been sort of doing, well, so, h of x then has negative, and then negative, and then positive. So what's happening at negative 1? We got a point of inflection there, right? Okay. Now, it's not 0 of the original function. Okay, so now we need to find h of x at negative 1 and at 1/2, and then see what's going on. Okay, so h of, what is it, negative 1? Negative 1 to the 4th plus 2 times negative 1 cubed minus 2 times negative 1 plus 5. So what do we got? 1 minus 2 plus 2 plus 5 gives us what, 6? So we've got the point negative 1, 6, right? And we know there's a point of inflection there. And then we've got h of 1/2. 2 times 1/2 cubed minus 2 times 1/2 plus 5. What do we got? 1/16. 1/4. So, what do we got? 4 and 5/16. Or what would that be? 69/16. Might not have, it's not bad necessarily to have the idea that it's 4 and 5/16, right? I mean, that way we know to stick it just a little under 4.5 if we're sketching this out. Okay, so sketching this out, what's this going to look like? So at negative 1, we've got 6. So there's put negative 1. This will be 1/2. What else can we do? We could do 0, right? Because 0, 5. So the y-intercept. So we've got 0, 5. We've got negative 1, 6, which is a point of inflection. And then we've got 1/2 and 4 and 5/16. Right, a little bit under 5 there. And that's our minimum, right? Okay, because we've got a negative slope and a positive slope, right? So negative positive gives you minimum at 1/2. So we're going to come down. down, have a point of inflection, drop through here, and go like that, something like that. And so, what did it ask for? Determine the local maximum and minimum value. So we have an absolute minimum. And local minimum at 1/2 and 69/16, and there are no local maximums, right? No local max. And once you've done that, then you could plug it into your calculator, right? If you wanted to, and just sort of graph it or stick it into a graphing program.
So I'm going to backtrack a bit. When you're taking the factors of h prime,
Yeah.
are you supposed to guess and check or use potential integral zeros?
Yeah.
So either one works?
Sure. Yeah. I mean, I just looked at it and said, hey, if I stick a -1 in there.
Okay.
So it's potential integral 0 just because the last factor was a 1, right?
Yeah.
Okay. And then I just looked at it, 1. Yeah, you can't plug it in your calculator and the thing, hey, on the deployment, let's just plug it in the calculator and look, there's a Yeah, I know, you don't have a calculator, right? So now you actually have to do what you were supposed to do all along.
What garbage.
Yeah. How did that happen? It's not. Yeah. How does that work? Okay, determine the critical numbers. So critical numbers are where what? G prime of x is 0 or does not exist. So what's first step? Prime it.
So is it often is prime the derivative of the outer box?
But then you would think chimpanzees and such should be good at calculus because they're primates. They're primates.
Oh.
All right. Yeah, not really, but. Oh, how does this work after a break? It's like what is it? F of x times g prime of x. So that's gonna be what? A half. Negative a half. Times 1. I'm not gonna write the 1, but it's because of the inner. Times 1. Oh. Plus. X plus 1 to the half. Okay, and now we need this factored, right? So we need a factored form. So we look for the lowest. So what have we got? We got like a 3 halves. So that's smaller than 6. So we'll take that out as a factor. So we got a 3 halves. We got an x squared and an x. So we'll take out the x. Okay, so we've dealt with this and this. And we got an x plus 1 to the negative a half. Okay, so that's our lowest common factor, right? 3 halves and an x plus 1 to the negative a half. So this guy is just going to be an x. And this guy is going to be, so 3 halves of something is 6. 3 halves of what? 12, 6, 4. 4, yeah, 4, right? It's 2 goes 3 halves of 4. So 1.5, right? Or you can just multiply this by 2/3, I guess, right? So 4, we've already taken care of the x, but we're going to have a full x plus 1. All right, we're almost there. So 3 over 2 root x plus 1, right? So let's put that there. And then we've got an x. And what do we have here? 5x plus 4. Okay, so how's that? Does that look good? Or right, I don't know how good it looks. So look right. All right, so that's step one, right? G prime of x. So when doesn't that exist? When x is -1, right? Because then we'll end up with the square root of 0, and yeah, nothing good can come from that. So g prime of x does not exist when x is -1. And when is g prime of x 0? So when x is -4/5 and 0, right? You don't do this, right? You just change the sign on this and stick it over that, right? So -4/5, so moving sides. All right, so we can construct a chart. And what's going to go in this chart? So, well, we don't really have to, we can't go below -1, right? Because g of x itself doesn't exist if x is less than -1. Although it does exist at -1. So that's a value we're going to need, right? Because that, remember we need the extremes, or the interval. So this is defined from g of x is defined from -1 up to infinity. All right, so we've got -1, -4/5, and 0. And factors, so we've got 3/2. We got a root x plus 1. We got a 5x plus 4. Taken all together, which will give us the sign of g prime of x, which will tell us the behavior of g of x. All right, so I'll do the easy one for you. Then I'll do the next easy one for you. If it's a square root, it's always positive. So really, it's only the 5x plus 4 that's going to have anything for us. That'll be plus, minus.
What? Don't you still need to account for an x?
Yeah, like the x.
You're right, there's an x. Yeah, so the 3/2, you're right. I missed an x. Ah. Okay, hang on.
It doesn't. I did that, so it's 3x, which is just
X, which would be what? Negative,
and then you got
negative.
that where it's going to be positive regardless.
Okay, good catch. That's why we do all that factored form stuff, right? This problem, it disappears off of this board. Like, it wouldn't happen to me on paper. Right? He says, looking at his paper, where it didn't happen to him. All right, so what do we got? Plus, minus, plus. So what's the first derivative test, which we actually do by just sort of sketching little arrows, right? If you're going from a positive slope to a negative slope, then you have a local maximum. And if you're going from a negative slope to a positive slope, you have a local minimum. And I don't have a lot more about that. Well, okay, 3x squared and then root x plus 1. So I got some idea maybe what this looks like. Like, it's always positive, right? Because this can't go negative. You can't get a negative out of the square root. You can't get a negative out of the x squared. Okay, so now we need some values. So we need g of -1, because that's an extreme, right? So remember on the interval, the local max and local minimum, well, really on the interval, I guess it would be an absolute max or min possible, right, on an edge. It couldn't be a local. Okay, but we want to graph this. Okay, so that's just 0. So we've got the point -1, 0. We need g of -4/5. And who makes these numbers up? What does that give us? Okay, so negative 4/5 and 48 root 5 over 125. Once I rationalize the denominator, right? Which, I don't know. And 0, right? G of 0. Okay, I'm not going to, G, because it's 3x squared, right? So 0. So G of 0 is 0. All right, so we've got a negative 1, 0. Which is, I think, an absolute minimum. Okay, so negative 1. So we had negative 1, 0 here. That's on the extreme edge. We got 0, 0. And we've got negative 4/5. 48 root, what's, let's call 48 50. So what's 50 over 125? It'd be divisible by, so it'd be like 2/5. 2/5, so like 0.4, and then root 5 is 2 something. 0.4, 2 something is about 0.8 something. I don't know. We probably build it. Let's just throw that in about here.
It's like 0.85865.
Okay, so
Approximately.
less than 1.
Oh.
All right, so what are we doing, right? So g of x is going up from negative 1 up to here, and then down to here, and then up to infinity and beyond, right? I mean, as the x's get really large, the 3x squared is going to get really large, and this isn't going to do much to keep it in check, because it'll still be fairly...
If G prime exists at 0, shouldn't it be curvy instead of a kink?
You're right. So,
Holy fuck, I'm a genius.
sorry, I did actually draw it curved, but I didn't draw it well curved. So, yeah. Okay, so we have an absolute minimum at negative 1, 0, and 0, 0. We have a local minimum at 0, 0. And we have a local maximum at negative 4/5 and excuse me, 48 root 5 over 125, right, which we figured out was less than 1. And that's what's going on here. Okay, so any questions? Right, we start with the function, we do the first derivative, we say where does it not exist, where is it 0, those are our critical numbers. We do up our little chart here to decide, okay, we need to look in these intervals, what's going on, what's the sign of the first derivative, and what does that tell us about the function, right? Function is increasing, decreasing, increasing, giving us local max, local min. And then on the edge, right, because negative 1. Determine the abs. I may have gone beyond, because what did they actually ask for? Intervals of increase. We never really specified the intervals of increase and decrease, so maybe we should do that here, right? So we'd say g of x is increasing. Where? From negative 1. And that's actually, it's defined at negative 1, right? So it's a square bracket. So from negative 1 to negative 4/5, a round bracket, and from 0 to infinity. And g of x is decreasing decreasing from negative 4/5 to 0. Alright, so I should make sure we answered. So determine the critical numbers, check. Intervals of increase and decrease, check. Local max and min, check. Determine the absolute minimum value where x is greater than 0. So f of x is x plus 1 over x, where x is greater than 0, the absolute minimum value. So we need f prime of x. X to, that's what? So negative 1 over x squared. So 1 minus 1 over x squared. Now it says x is greater than 0, right? Because this is not defined at 0, but that's fine because we're asked to find where x is greater than 0. So where are the zeros? Or where is the 0, I guess? Yeah. So in the given interval, f prime of x exists everywhere, and f prime of x is equal to 0 when x is equal to 1. Okay, so we just got to figure out what's going on from 0 to 1. Write that down. And from 1 beyond. And all we really have going for us is there's no factor, right? It's just 1 minus 1 over x squared. So between 0 and 1, 1 minus, so if we had like a half squared would be a quarter, but then that would be flipped and be a 4, would be 1 minus 4, so that would be negative. And anytime we get bigger than 1, this will just get smaller and smaller and smaller, right? So that'll be positive. So we got a down and an up, right? So that tells us here we have a minimum. Determine the absolute minimum value. Okay, so we've got a minimum when x is equal to 1, f of 1 is equal to 2. So 1, 2, we have an absolute at 1, 2. Yes?
Wait, wouldn't f prime of x equal 0 when x equals negative 1 as well?
It would, but what's our
Oh, duh.
our interval is from 0 out. No, you're right? Because the function exists, right? It doesn't exist at 0, but it does exist either side. Okay, but this is like doing a trig one. So they just say, hey, between 0 and 2 pi, right? Like, you know, just do it in one period. It's just going to repeat after that. Yeah, so it's just kind of watching out. So if we looked at, well, what does this look like? So, I mean, 1 plus, so as x gets small, 1 over x gets pretty big, right? So we've got, what, 1 and we've got 2. So it's going to kind of come down, right? Because it's coming down. Between 0 and 1, it's coming down. So that's going up there. And then it's going to head back up again. Okay. Rough sketch. Right? First derivative test for absolute extreme values. Let C be a critical number of a continuous function f, right? So critical number means the first derivative is 0 or does not exist, right? If f prime of x is positive for all x less than c and is negative for all x greater than c, so it's positive for all x below and negative for all, then f of c is the absolute maximum. And if f prime of x is negative, I'll just do that the same, but I'll turn around, is negative for all x's, yeah, if you're doing it with your hands, you gotta do it yourself. Then it's the absolute minimum, right? Okay, and keep in mind, we're capturing that down here. So, that kind of points the way for you. All right. Even and odd functions. Even functions. These functions are even. What is the symmetry in each of the following functions? They're symmetrical about the y-axis. Symmetrical. And we've got x squared, we've got 3 cos x, and we've got the absolute value of x. Functions with this kind of symmetry are said to be even functions. In other words, even functions are functions that are symmetrical about the y-axis. Which, if you pronounce that as y-axis, it might actually come out as kind of the same as y-axis. Examine the graphs above. Compare the value of each function at x equals 1 and x equals negative 1. X equals 1, x equals negative 1. X equals 1 and negative 1. X is 1, negative. Complete the following. So if f of 1 is equal to k, then what's f of negative 1? K. Or in general, if f of x is equal to k, then f of negative x is equal to k. Right? It's a function. When x is replaced by negative x, you get a reflection across the y-axis, right? Remember transformation e stuff. So the function f of x is an even function if and only if f of negative x is equal to f of x. Right? So I mean, if you look at it as a transformation, if it's a reflection across the y-axis, then x has been replaced with negative x, right? And so f of x is equal to f of negative x, or vice versa. Show algebraically that the functions shown above, I think these are below. Oh, or no, that's true. Functions shown above are even by using their equations, which are below. All right, so what we're going to do is, well, we're going to say, what's f of negative x? It's negative x quantity squared. What's negative x quantity squared? X squared. What's x squared equal to? So x squared is just f of x, right? So f of negative x is equal to f of x. Okay, f of negative x for this is 3 times the cosine of negative x. Now we want to show that that's the same, so we're going to do this. We'll say it's 3 times the cosine of 0 minus x. Right. So what's negative x? Well, you could write that as 0 minus x. Okay, now we have the cosine of a difference, right? Which is cos. So it's 3 times, okay, so it's cos 0 cos x plus sine 0 sine x. Now, what's the cosine of 0? 1. How much detail do we want to show? So 1 times cos x, what's the sine of 0? Plus 0 times sine x, which is equal to 3 cos x, which is equal to f of x. So we have shown that f of negative x is equal to f of x. Therefore, it is an even function. Therefore, it is a reflection across the y-axis, right? f of x is equal to the absolute value of x. What's f of negative x? Absolute value of negative x. What's the absolute value of negative x? The absolute value of x, which is equal to?
It's absolutely not. It absolutely is.
It's absolutely even. Okay, so then these are all even functions, right? By definition.
I'm not saying that.
Odd functions. Describe the symmetry in the following functions. So,
They're mirrored along there. There. Just kidding. They're rotated 180 degrees.
Yeah.
Exactly. Is that true? Is that? Oh.
no, it's true.
I would agree.
It's a rotation. So it's symmetrical about 0, 0, right? Which is a rotation of 180 degrees, right? So symmetrical about 0, 0, or about the origin, I guess. Symmetrical about the origin. Okay, which is 0, 0. And another way to say that is it's rotated 180 degrees about the origin. Okay, say, or rotated which is still 0, 0. All right, so what do we got? X cubed, right, which we're familiar with. We've got 3 sine of x, and we've got the cube root of x. Functions with this kind of symmetry are said to be odd functions. In other words, odd functions are functions that are symmetrical about the origin. Okay, or 0, 0.
Absolutely, let's play.
So compare the value of each function at x equals 1 when x equals negative 1. So 1. 1 and negative. Complete the following. So if f of 1 is equal to k, then f of negative 1 is negative k. Or in general, if f of x is equal to k, then f of negative x is equal to negative k. So the function is an odd function if and only if f of negative x is equal to
Negative. Oh, negative.
negative f of x, right? So if f of negative x is equal to the negative of f of x, right? Where it's an even function if f of negative x is just the same as f of x. Show algebraically the above functions are odd by using their equations. Okay, so we're looking at f of negative x. So the way, if we're just given a function, we don't know if it's even or odd. We're going to just evaluate and just say, okay, what's f of negative x? Okay. Now, if it comes out to be the same as f of x, then we'll say it's even. If it comes out to be the negative of f of x, then we say it's odd. And if it comes out to something completely different, then we'll say it's neither even nor odd. Okay, so f of negative x is the negative of x cubed, okay, which could be written as negative 1 cubed x cubed, or negative x cubed. And we could say that by saying, well, that's negative of f of x. So in this case, f of negative x is the negative of f of x, right? The negative of f of x. 3 sine x. Okay, so we're going to run through the same thing we did with cosine, right? Only we're going to use sine. So it's 3 times the sine of negative x, which is 3 times the sine of 0 minus x, which is 3 times. Okay, so what's the formula for sine a minus b?
It's sine of A plus B.
Sine A equals B.
Sine.
Minus equals A sine B.
So sine A, sine 0, cos B, cos x, and then is that one a plus or minus, right? That retains its sign. Minus cos 0 sine x. Okay, sine of 0 is 0, so we get 0 times cos x minus the cos of 0 is 1. So it's 3 times negative sine x. Let's just call it negative 3 sine x, which is the negative of f of x. So f of negative x is negative f of x. So f of x is equal to the cube root of x. So f of negative x is the cube root of negative x, which is equal to the negative cube root of x, right? We can always pull a negative sign under a cube root out front, which is negative f of x. So f of negative x is the negative of f of x. Now we got what? 3 to do where we don't know what they are. So determine whether each function is even, odd, or neither, and describe the symmetry. Okay, so in any case, we have to, if you want to determine whether it's even or odd, you've got to evaluate f of negative x. So everywhere we see an x, we're going to replace it with negative x. All right, so I've got negative x to the power of 5, which is negative x to the 5th. Minus negative x, which is plus x. And negative x quantity squared is just x squared, right? So we got 1 plus x squared. Now we've got, pull out the negative. Yeah. So if we factor out a negative, then this will become positive x to the 5th minus x over 1 plus x squared, which is negative. Well, that's that. So it's negative f of x. So if f of x is negative f of x, then this is odd. It's odd. So it's symmetric about the origin. G of x. So we're going to have to work out g of negative x. Which means we're going to go in here, and everywhere we see an x, we're going to replace it with negative x. I guess I could remove these brackets if I wanted to. So let's factor in negative 1 out of that first set of brackets, and this will become x plus 1. Let's factor in negative 1 out of this set of brackets, and this will become x minus 1. Got the two negatives, so they're just going to be positive, so this will just be x plus 1, x minus 1. And how does that compare to the original function? It is the original function, right? So g of negative x is equal to g of x, which tells us it's an even function, and it's symmetrical about symmetrical about the y-axis. h of x is 2x over x plus 3. So h of negative x all right, so I could factor a negative out of the bottom. And those guys will cancel. So how do these two guys compare? Yeah, they're not equal, and it's not the negative of the. So h of x is neither, or sorry, h of negative x. Turn that in. H of negative x is not the negative of h of x, nor is it. Nor is it. It's not the negative of h of x, so it's not odd. Nor is it equal to h of x, so it's not even. So it's neither. Neither. So there is neither rotational symmetry about the origin nor symmetry about the y-axis.
I was so confused.